March 2026. A photocenter shifts by 0.3 arcseconds between Tuesday and Thursday. The shift persists across 4 telescopes, 2 hemispheres, 5 reduction pipelines. The predicted position, calculated from 100 prior measurements, gravitational physics refined to 15 decimal places, misses. Not by much. Just enough. The brightness curve doesn't match the phase angle. The tail bends 7 degrees off the antisolar line, then straightens, then bends again. A faint asymmetry in the coma repeats every 41 hours, but the spectral lines don't show rotation. The object is 3A Atlas. The update is small, but NASA's tracking solution just revised the non-gravitational acceleration term upward by 18% for the 3rd time in 60 days. Here's the question: are we watching a dirty snowball with messy physics, or a trajectory being corrected in real time by something we haven't modeled? The numbers don't lie, but they also don't explain themselves. On a cold server in Pasadena, a new orbital fit replaces the old one. The change is invisible to anyone not watching the ephemeris files. No press release. No headline. Just a quiet substitution. State vectors updated, uncertainty ellipses tightened, residuals redistributed across the arc. For most objects, this is routine. Asteroids drift slightly as more data arrives. Comets outgas, and models adjust. Tracking updates are the pulse of celestial mechanics. Constant, iterative, expected. But 3 Atlas is not most objects. It arrived from interstellar space in early 2025, detected first as a faint streak in Pan-STARRS survey frames, then confirmed by follow-up observations from Mauna Kea, the European Southern Observatory, and a dozen capable amateur setups across 3 continents. Its hyperbolic orbit was unmistakable. Eccentricity greater than 1. No return trajectory. A visitor, not a resident. The 3rd confirmed interstellar object in human history, following on Oumuamua in 2017 and Tuati Borisov in 2019. Unlike Oumuamua's enigmatic silence, 3E Atlas showed a coma. That should have made it easier to understand. It didn't. The initial orbital solution placed it on a clean hyperbolic path, inbound from the direction of Cassiopeia, approaching perihelion near 1.40 in late 2026. As weeks became months, more telescopes joined the campaign. Astrometry poured in, high-precision positions, sub-arcsecond accuracy, time-stamped to the millisecond. The orbital elements tightened. Uncertainty ellipses collapsed from hundreds of kilometers to tens, then to single digits. Everything was going as expected. Then the residuals started to grow. A residual is the difference between where an object should be and where it actually is. For a well-modeled orbit, residuals shrink as data accumulates. They scatter randomly around 0, averaged out by noise, calibration errors, atmospheric seeing. But 3I Atlas began showing a pattern. Positions consistently ahead of prediction. A small but persistent offset, growing slowly, systematically, across consecutive nights. At first, it looked like a data artifact, maybe a catalog bias, a bad star field, a centroiding error in the reduction pipeline. Teams checked their work. Different telescopes, different detectors, different software. The offset remained. So they added a non-gravitational term to the model. This is standard practice for active comets. Outgassing produces thrust, a tiny rocket effect, as sublimating ice ejects gas and dust asymmetrically, pushing the nucleus in one direction. Comets don't obey pure Keplerian orbits. They accelerate. The acceleration is small, microns per second squared, sometimes less, but over weeks and months, it adds up. You model it with a radial and transverse component, tied to heliocentric distance, tied to how fast the surface heats and cools. You fit those parameters the same way you fit orbital elements: least squares minimization, iterative refinement, convergence. The fit improved. Residuals dropped. Problem solved. Except the parameters didn't stabilize. Every new batch of astrometry required a new non-gravitational solution. The acceleration term kept changing, not refining, but shifting. Upward, mostly. 18% in the latest update. That's not how cometary outgassing behaves. Once you're far enough along the arc, once you've captured perihelion approach and the thermal curve, the parameters should settle. They don't vanish, but they don't wander. Physics is physics. Heat in, gas out, momentum transfer. The equations are known. But 3I Atlas wouldn't sit still in the model. The tracking update that arrived this month revised the solution again. Same orbit, slightly different forces. The revision propagates forward through every future prediction, where the object will be in April, in June, at closest approach to Jupiter in September. Ephemerides shift by fractions of a degree. Visibility windows change by hours. Observation campaigns adjust their schedules. And quietly, carefully, the question changes too. It's no longer is the orbit accurate? It's why does the orbit keep needing correction? The update isn't about the object changing in space. It's about our model finally admitting what the object has been doing all along. By now, 8 independent observatories have published astrometry. Mauna Kea, ESO's Very Large Telescope, Subaru Tatafontanadisha, Gemini North, Tatsideta Shamadhatin, Wananiyomoye, the Las Cumbres Observatory Global Network, veteran amateurs in Spain, Australia, Arizona, stacking dozens of frames per night, achieving positional precision that rivals professional work. Each dataset is reduced separately. Different reference catalogs, Gaia Draw 3, Thomas, Pan-STARRS, DR2, different centroiding algorithms, Gaussian fits, moment analysis, PSF photometry, different calibration frames, different flat fielding, different cosmic ray rejection. The offset persists across all of them. This is the first filter. If an anomaly appears in one dataset and vanishes in another, it's probably an artifact. Systematics leave fingerprints. A bad reference catalog shifts all objects in a field the same way. A tracking error smears stars into streaks. A miscalibrated photometric 0 point changes brightness, not position. When you see the same residual in Subaru data and amateur data, processed on different continents with different software, you stop blaming the tools. You start looking at the object. So teams went deeper. They examined FITS files directly, raw frames, not just processed catalogs. They checked background subtraction, was scattered light or nebulosity biasing the centroid. They verified that the photocenter, the brightness-weighted center of the coma, wasn't being pulled off nucleus by symmetric dust. They ran synthetic star tests, injecting fake objects into real frames to confirm that centroiding worked correctly. They cross-matched observations taken hours apart, looking for any hint of periodic motion, rotation, precession, tumbling that could create an apparent displacement. Nothing explained it. The photocenter offset is real. It's small, typically under half an arcsecond, but it's measurable, repeatable, and consistent. At 3 Atlas's current distance of roughly 3.0, half an arcsecond corresponds to about 1,500 kilometers. That's not nothing. That's a spatial structure. A displacement between where the light is brightest and where the nucleus, the solid body, should be. And the brightness curve won't cooperate either. Photometry from 4 different groups shows the same irregular behavior. The object brightens and dims on a time scale of roughly 41 hours. But the amplitude varies unpredictably. Some maxima are sharp, others broad. Some minima are flat, others show secondary dips. Phase angle corrections don't fix it. Heliocentric distance corrections don't fix it. If it's rotation, a spinning nucleus with bright and dark patches, the light curve should be stable over time. It isn't. If it's activity, jets turning on and off, the spectroscopy should show variability in gas production. It doesn't, not consistently. Spectroscopy adds its own puzzle. Multiple observations in optical and near-infrared wavelengths detect CN, C2, and O emission, the classic cometary signatures of sublimating carbon and oxygen-bearing ices. The gas production rates are modest, consistent with a small active fraction on a nucleus a few kilometers across. But the emission lines are broad, and their centroids don't shift the way you'd expect from a rotating source. The Doppler pattern is there, but it's messy, smeared, as if the gas isn't coming from a single spinning nucleus, but from multiple sources with slightly different velocities. Then, there's the tail. Images from wide-field surveys and targeted campaigns show a classic dust tail stretching anti-sunward, broad, diffuse, gently curved by radiation pressure. But in high-resolution frames from Subaru and the VLT, the tail shows a subtle twist. Near the nucleus, the dust direction points about 7 degrees off the projected anti-solar line. Farther out, it corrects. The deviation is small enough to ignore if you're not looking carefully, but persistent enough that 3 independent image analysts flagged it in their reports. Solar radiation pressure and solar wind interaction can create curved tails, especially if dust grains have a range of sizes and ejection velocities. Large grains fall behind, small grains race ahead. The tail becomes a fan, not a line. But the 7-degree offset is in the wrong direction for that geometry. It doesn't match the models. Every anomaly in isolation is plausibly mundane. A centroid offset, maybe asymmetric outgassing. An irregular light curve, maybe complex rotation. A misaligned tail, maybe unusual grain properties. Broad spectral lines, maybe turbulence or multiple jets. Wandering non-gravitational parameters, maybe evolving activity. But together, they form a pattern. Pattern of small, persistent contradictions that don't resolve when you clean the data harder. And that's when the update stops being routine. Physics is patient. It doesn't care if the story is confusing. It simply describes what happens when matter and energy interact under known forces. For a small, icy body approaching the sun, the script is well rehearsed. As heliocentric distance decreases, solar flux increases. Surface temperature rises. Ice sublimates. Water, carbon monoxide, carbon dioxide, methane, ammonia, depending on composition and depth. Gas escapes through cracks and pores, dragging dust grains into space. The gas expands supersonically, forming a coma, a temporary atmosphere, tenuous and glowing, lit by scattered sunlight and fluorescent emission. Dust grains decouple from the gas within seconds to minutes, depending on size. Small grains, microns across, follow the gas flow. Large grains, millimeters or more, move ballistically, governed by their initial velocity and solar radiation pressure. The dust tail forms. The ion tail, if the gas production is high enough, streams away along magnetic field lines carried by the solar wind. The nucleus, buried beneath the coma, remains mostly invisible. Perhaps a few pixels across even in the best telescopes, often unresolved entirely. We infer its properties indirectly. Size from thermal emission, or absolute magnitude, rotation from light curve periodicity, albedo from brightness and distance, mass from density assumptions and volume estimates. And from all of this, we calculate non-gravitational acceleration. The recoil force from outgassing is straightforward to model in principle. Gas leaves the surface at a few hundred meters per second, carrying momentum. By Newton's third law, the nucleus feels an equal and opposite force. If outgassing is symmetric, uniform across the surface, or at least averaged over a rotation period, the net force is radial, pointing away from the sun. If it's asymmetric, concentrated in jets, or lagging behind the subsolar point due to thermal inertia, there's a transverse component too, perpendicular to the sun object line. You write this as an acceleration proportional to solar flux, declining as 1 over distance squared, modified by empirical scaling factors that capture the efficiency of momentum transfer. You fit those factors to the astrometry. If the model is good, the residuals shrink. If the object behaves like a normal comet, the parameters stay constant as more data arrives. 3. Atlas doesn't. The radial component keeps increasing. The transverse component fluctuates. The fits converge mathematically, but the parameters drift. You can force a stable solution by restricting the data arc, using only the last 60 days for instance, or only observations after a certain heliocentric distance. The fit improves. But that's not a physical explanation. That's admitting the model only works locally, only temporarily. Physics doesn't change every 2 months. So you check the assumptions. Maybe the mass estimate is wrong. If the nucleus is smaller than expected, the same outgassing produces more acceleration. But the brightness and thermal emission constrain size pretty tightly, somewhere between 3 and 6 kilometers, depending on albedo. Even the most extreme assumptions only shift the acceleration by a factor of 2 or 3, not enough to explain the drift. Maybe the activity is evolving faster than expected. Seasonal effects, changing illumination as the rotation axis processes, can turn jets on and off, modulating gas production. But seasonal models predict smooth changes over weeks to months, not the erratic behavior seen in the light curve and spectroscopy. Maybe the composition is exotic. Supervolatiles, carbon monoxide, nitrogen, methane, sublimate at much lower temperatures than water ice, producing strong outgassing far from the sun where water remains frozen. Delayed thermal waves, heat diffusing into the interior, releasing gas hours or days after peak illumination, can create phase lags and complex torques. But 3, Atlas, is already inside 3O, well into the water ice sublimation zone. The spectroscopy shows CN and O, not exotic volatiles, dominating the gas production. Maybe the nucleus is fragmenting. A breakup event would scatter multiple pieces, each outgassing independently, creating a composite photocenter and unstable dynamics. But there's no clear evidence of fragmentation in the images. No secondary condensations, no expanding debris cloud, no sudden brightness surge. Just the persistent, low-amplitude irregularities. Maybe the dust is strange. Fractal aggregates, porous, low-density clumps of tiny grains, scatter light differently than solid particles. They can create unexpectedly bright comet with relatively little mass, distorting estimates of dust production and momentum transfer. Unusual grain size distributions, deficits of small particles, or excesses of large boulders can twist the tail geometry and the scattering phase function. But there's no direct measurement of grain structure. Only models fitted to brightness and color, which always carry degeneracies. Every explanation is plausible in isolation, but none of them predicts all the anomalies at once. None of them explains why the tracking solution needs constant revision. The physics isn't wrong. The physics is incomplete. Residuals are a map. They show you where your model fails. For 3I, Atlas, the map has 3 landmarks. First, the astrometric residual pattern. Positions consistently ahead of prediction, by margins that grow and shrink but never vanish. When you fit a non-gravitational acceleration model, the residuals drop, but only temporarily. The next week of data requires a different acceleration. The week after that, another. The pattern suggests force, but not constant force. Not simple force. Force that varies on timescales, shorter than the thermal response of a kilometers-wide ice ball. Second, the photocenter offset. The brightness peak sits 1,500 kilometers, give or take a few hundred, away from the predicted nucleus position. This persists across multiple epochs, multiple instruments, multiple reduction methods. If it were a data artifact, it would vanish when you change the calibration. It doesn't. If it were random noise, it would average out. It doesn't. It's a real spatial structure. Something bright, offset from the nucleus, stable enough to measure night after night. Third, the morphological misalignments. The tail near the nucleus points 7 degrees off the antisolar line. The brightness varies on a 41-hour timescale, but the spectral lines don't show coherent rotation. The gas production is steady, but the dust output seems modulated. The coma asymmetry repeats, but the emission centroids don't shift predictably. Individually, each could be noise or complex geometry. Together, they resist a single coherent explanation rooted in standard cometary behavior. These aren't proof of anything except that the baseline model, a single solid nucleus, outgassing according to thermal equilibrium, responding predictably to solar forcing, is insufficient. So you build the next model. Start with extreme but ordinary physics. A nucleus with highly asymmetric outgassing, one hemisphere active, the other dormant, producing a sustained off-axis thrust. Complex rotation, precession, nutation, tumbling, creating time-varying torques, and constantly shifting jet directions. Seasonal illumination. The rotation axis tilted such that different regions heat and cool on long timescales, cycling through active and dormant phases unpredictably. This can produce variable non-gravitational terms. It can create brightness fluctuations. It can offset the photocenter if the active region is far from the center of mass. But it requires fine-tuning. The rotation period has to be just right. The jet locations have to be arranged just so. The albedo contrasts have to be extreme. Possible, but improbable. And it still doesn't explain the tail misalignment or the spectral line widths. Next layer, exotic materials. Assume the nucleus is rich in supervolatiles, carbon monoxide ice, dominant at the surface, sublimating vigorously at large distances. This increases gas production and non-gravitational acceleration beyond water ice predictions. Add in delayed thermal response. Thick, insulating dust mantles trapping heat, releasing it hours after sunset, decoupling activity from instantaneous solar forcing. This creates phase lags and erratic outgassing. This helps with the variability. It makes the acceleration less predictable, but it requires composition wildly different from typical comets, or from Toy-Borisov, the previous interstellar comet, which looked spectroscopically normal. Interstellar objects should sample different formation environments, different stellar neighborhoods, different chemical histories. Exotic composition is plausible, but it's a free parameter, not a prediction. Third layer, structural complexity. Imagine the nucleus isn't a monolith, but a rubble pile. A loose aggregate of smaller fragments, held together by weak gravity and friction, outgassing from multiple active patches. Or a contact binary. Two lobes, different compositions, different thermal properties, each contributing differently to the total acceleration. Or a recent fragmenting event, the nucleus cracking, shedding pieces too small to resolve individually, but large enough to affect the photocenter and light curve. This can produce the photocenter offset naturally. Multiple sources of light, slightly separated, create a composite brightness peak offset from any single solid body. It can explain light curve irregularities, fragments rotating independently, overlapping and interfering. It can explain tail misalignments, different fragments ejecting dust in slightly different directions. But fragmentation leaves evidence. Expanding halos. Secondary nuclei. Brightness surges. Trails. The images of 3 Atlas show none of these clearly. Either the fragmentation is subtle, gentle, slow, controlled, or it's not fragmentation at all. Fourth layer, swarm physics. Not fragmentation, but a persistent aggregate, a collection of loosely bound or unbound objects, dust clumps, or porous structures moving together in a coordinated way. Not because of intent, but because of shared origin or dynamical coupling. Each piece outgasses weakly. Together, they produce a diffuse, extended source that looks like a single comet from far away, but behaves erratically up close. This is a boundary hypothesis. It's physically possible. There's no law against a gravitationally unbound swarm of small bodies traveling together on similar orbits, especially if they were ejected from a common source. But it's rare. And it requires that 3 Atlas isn't a comet. It's a debris field that looks like one. Fifth layer, propulsion-like models. Set aside natural mechanisms for a moment. Ask, what would the data look like if the acceleration weren't passive outgassing, but active thrust? Controlled, directed, variable. The signature would be clear. Acceleration vectors that don't align with solar forcing, magnitudes inconsistent with plausible mass loss rates, changes synchronized with geometry rather than temperature, energy budgets that require internal sources. 3i, Atlas doesn't show this yet. The acceleration is still broadly consistent with outgassing physics, just messier and less stable than expected. But the boundary is defined now. If future data shows sustained transverse acceleration with no thermal explanation, if the energy budget fails, if the force vectors decouple from solar distance, Then the hypothesis graduates from speculative to testable. Extraordinary interpretations require extraordinary, testable evidence. The update gives us neither proof nor dismissal. It gives us sharper questions. April 2026. The object crosses 2.50 inbound. Solar flux increases by 20%. Thermal models predict a corresponding rise in outgassing. If the non-gravitational acceleration is driven by sublimation, it should scale predictably. Observations scheduled. Photometry every clear night, spectroscopy twice per week, high-resolution imaging at closest phase angle. June Ditak. Perihelion approach. 1440 from the Sun. Peak activity. If there's a breakup or a major jet activation, it happens now. Multi-longitude campaigns coordinated. Australia, Chile, South Africa, Hawaii, ensuring continuous coverage as Earth rotates. The goal: catch any transient event, any sudden change in brightness, morphology, or spectral output. Measure the rotation period definitively, if it exists. Map the coma asymmetry in time and space. September. Close approach to Jupiter, not a collision, but a gravitational interaction, passing within 0.80 of the giant planet. This is the dynamical laboratory. Jupiter's gravity is immense. If 3I Atlas is a single solid body, the trajectory will bend predictably, calculable to the kilometer. If it's a swarm, the pieces will spread, subtly, measurably. If there's any anomalous acceleration, any thrust not explained by outgassing, the post-Jupiter orbit will deviate from the prediction. The predictions are already written. Ephemerides extended, uncertainty cones calculated, residual thresholds defined. If the astrometric offset continues to grow, if the non-gravitational term keeps escalating, if the photocenter displacement persists through perihelion, the baseline model is falsified. Not discarded. Science doesn't discard, it refines. But insufficient. If the tail misalignment remains, if the spectral lines stay broad and erratic, if the light curve never stabilizes, then structural complexity becomes mandatory. Not optional. Not exotic. Required. If the Jupiter encounter shows trajectory deviation beyond the expected gravitational perturbation, beyond plausible outgassing corrections, beyond every conservative extension of cometary physics, then the hypothesis space narrows sharply. And if everything resolves, if the activity smooths out, if the residuals collapse, if the tail straightens, and the photocenter locks onto the predicted position, then the anomalies were transient. Artifacts of incomplete data, early observational challenges, models not yet converged. The story becomes a lesson in patience, not mystery. Both outcomes are scientific victories. Mystery resolved is knowledge. Mystery deepened is direction. Astronomy is the discipline of delayed gratification. You ask a question, point the telescope, collect the photons, wait months or years for enough signal to analyze, publish the result, wait for someone else to confirm or challenge it, refine the model, ask the next question. There are no instant answers. No real-time experiment where you change one variable and watch the effect immediately. The objects are too far, the timescales too long, the signals too faint. 3I Atlas will not explain itself on demand. It will drift through the inner solar system at 16 kilometers per second, outgassing or not outgassing, accelerating or not accelerating, fragmenting or not fragmenting, obeying physics we understand or physics we've missed. The photons it emits will travel for minutes or hours, strike detectors across the planet, get recorded as arrays of numbers, reduced, calibrated, archived, analyzed. The measurements will accumulate. The models will iterate. The residuals will shrink or grow. And we will watch. The update is not an ending. It's a revision, one of many, past and future. Orbital elements are never final until the object leaves observability forever. Even then, the solution is only final in the sense that we stop updating it, not because we've captured every force, every influence, every perturbation down to infinite precision. We never observe the object directly in full. We observe its effects on photons and pixels and residuals. We infer its properties through layers of modeling, calibration, assumption. The nucleus, if there is a single nucleus, remains hidden beneath coma and dust, a few kilometers of ice and rock we cannot touch, cannot sample, can only glimpse indirectly through the light it scatters and the gravity it exerts. This is the condition of all astronomy. Distance transforms certainty into inference. We build confidence through consistency, through independent confirmation, through falsifiable predictions tested over time. We live with unfinished answers not because we are careless, but because the universe is large and we are patient. The same details that opened the story remain. A photocenter offset, a non-gravitational term that won't stabilize, a tail that bends slightly wrong, a brightness curve that resists simple explanation, a spectral signature that hints at complexity we haven't resolved. These are not narrative twists. They are data. And data, given time, becomes understanding, or better questions. If 3I Atlas is ordinary, it will teach us how ordinary can look strange when viewed incompletely. If it is extraordinary, it will teach us where the boundary lies between known and unknown physics, and what it takes to cross it. Either way, the next round of observations will matter. April's activity surge, June's perihelion images, September's Jupiter encounter. Each a checkpoint, each a test, each an opportunity for the models to prove themselves or break. The update that arrived this month is already obsolete. New astrometry is being reduced tonight. New photometry will post next week. New spectroscopy waits for the next clear sky, the next allocation of telescope time, the next batch of photons crossing 3 astronomical units to meet silicon detectors and careful eyes. The object doesn't know we're watching. It doesn't care. It moves through space, according to forces we name with equations. Forces we approximate with parameters. Forces we measure with residuals. And somewhere in those residuals, quiet and persistent, is the truth. We'll find it, or it will find us. For now, we wait. We watch. We revise. And the numbers, patient as starlight, keep arriving.